Fortunately, the other three couldn't be here, so I get to give the talk. Okay, so where are we pushing the formal methods, right? So the Linux kernel has an ecosystem called the eBPF ecosystem. It allows arbitrary users to extend the Linux kernel without knowing the without being a kernel developer. Okay, so eBPF is a virtual instruction set in which you write programs and you can extend the kernel. And you don't have to write assembly, like you can write it in high level programs of your choice, C, Rust, even like many of the dynamic languages. So if you talk to people in the networking, it's like superpowers have come to Linux. Like, this is the title of a blog post by Brendan Gregg, an engineer at Netflix. And now with cloud native environments, BPF is becoming everywhere. Like there's so much about BPF. And we all know the ramifications of running arbitrary code in the kernel, right? And kernel developers are not dumb. So they're very smart, they care about the security. So what they do is Linux kernel has an abstract interpreter in a production system. So typically when we analyze programs on the side. When the program is safe, we deploy it in production. And now we have an abstract interpreter, a static analyzer running in production and running on 6 billion devices. And what do you do when the user wants to inject a code into the kernel with a BPF system call? The abstract interpreter kicks in. They call it the BPF verifier. And when the BPF verifier deems the program to be safe, that's when the program is JIT compiled into x86 or ARM and attaches to the hooks at various places. And now you have extensibility. And now what does this abstract interpreter do? BPF is not Turing complete, so you cannot write uncounted loops, so you only have bounded loops. So it symbolically evaluates every path and makes sure every memory access is within the bounds of the kernel buffers. And since it's a bounded program, it also wants to prove termination. And finally, no illegal instruction fault can occur. And recently with Spectre and Meltdown, people have added like a lot of mitigations to avoid side channel, to ensure side channel freedom, prevention from side channel errors with Spectre and Meltdown. So we all know this writing a static analyzer is hard. Then this BPF verifier has been subject to a lot of vulnerabilities. When we started this project 6 years ago, our goal was, can we verify this verifier? What are the algorithms that these kernel developers are using? There was no documentation. Code is the documentation, right? So we wanted to figure out what are the algorithms and can we verify it, like just as a curiosity project. And today, 6 years hence, like we have built Agni. So this is our automated verification of the eBPF verifier in the Linux kernel. And the important thing why you should be excited, why we are excited about it, is because it's part of the Linux continuous integration testing infrastructure today. The Linux kernel developers have been using it for the last 1 year. If you add a new abstract operator to the kernel, it will be checked by Agni today. Okay, so I'm going to describe what Agni is, just to give you, just to get everyone on the same page. So what is Agni? So the eBPF verifier is about 30,000 lines of C code. This is what the static analyzer is. And out of this 30,000 lines of C code, about 6,000 lines are the abstract operators. So kernel uses C, but it uses a pretty decent version of C. So avoiding undefined behavior, it needs to be portable. So now we want to analyze it. These are the implementations of abstract operator. We need to convert them into verification conditions in first order logic. So what do we do? So one of the challenges in analyzing kernel code is you have headers, kernel headers, and how do you analyze them? And this is where our group's expertise in compilers comes into the picture. So you have kernel, whatever version you are looking at, it has to be compiled by some compiler. And when the compiler actually compiles it, it pre-processes all the headers. So we rely on the LLVM compiler. We take the kernel source code. This is our ground truth, the implementation of the verifier. We automatically compile it with appropriate headers, and we get the LLVM IR. Now we have a very verbose representation of the kernel's implementation of the abstract operators. And we don't want to handle all at once. Divide and conquer is the rule of the world. So what do? So we want to just slice out a BPF AND operator, the abstract operator for AND or abstract operator for multiplication. We use constant propagation and dead code elimination to do this. And we have custom memory SSA analysis and other custom passes that we have to generate a verification condition from the LLVMIR. So at the end of it, from the kernel code, we have the encoding of the abstract operator in first order logic. Okay? Then we define the specification of what does it mean for an abstract operator to be correct. If you have forgotten, like don't worry, like in the next slide I'll tell you what is the specification of correctness is. Okay? So now if our verification deems the operator to be unsound. So telling the kernel developers, oh, your operator is unsound is useless, like, oh, you wrote some, you had some fancy abstractions and now you're saying unsound, like give us concrete things. So to enable kernel developers to debug this program, we produce a concrete BPF program that you can plug in to the kernel and show the difference in the abstract and the concrete semantics. So this is what we call as a proof of concept program, and you can boot up a Linux in your QEMU emulator and show the difference in the semantics. This entire infrastructure was essential to push Agni into the CI of the Linux kernel. Okay? So now fast forward 6 years and Linux kernel developers have been using Agni for a year or so. Okay? So now what happens is you have like sound operators being committed. And so before I go further, like I promised you, like what does it mean for an abstract operator to be sound, right? When is an abstract operator, when do you call an abstract operator is sound? So what is an abstract operator? So you have a concrete variable in a program, let's say an addition operation. It takes two concrete inputs and produces a result z. So it takes two inputs x and y and produces a result t. Corresponding to this concrete operation, you model the state of the variable with an abstract domain. It could be a bitwise domain where you model each variable as a sequence of bits where every bit is a known 0, known 1 or an unknown, and or it could be model it as an interval where like a value is between this interval. So the abstract input state for an abstract operator P and Q are these intervals or bitwise domains. Kernel uses 5 abstract domains, 4 intervals and 1 tri-state domain to perform the static analysis. So let's say we have an abstract operator which takes P and Q as inputs and produces an abstract state R as the output. So there is a corresponding concrete operation, this is the concrete addition, which takes x and y as input and produces z as the output. So we want our inputs to be well formed. So what does it mean for an input to be well formed? Input x and y, the concrete input x is a member of abstract input state P, and concrete input y is a member of abstract input state Q. It better be the case that your concrete output z is a member of output abstract state R. Now we are wondering how do we encode this membership predicate in first order logic. So if you have an interval, like interval can be represented using two integers, which is a lower bound and the upper bound. We can encode the membership predicate by saying x is greater than or equal to the lower bound and less than or and also less than or equal to the upper bound. Okay, this is your membership predicate. So now what we have sound operators coming in. So this is what Agni uses. This is our specification of soundness. Like you can read our papers. There is like a lot of caveats about how kernel does reduction and various other things. So just to give you an idea of the formula. So all we have, this is the SMT conditions that we generate for all input states P and Q, for all concrete values x, y belonging to 64-bit integers. So x is a member of P, y is a member of Q, z is the concrete result that the operation produces. And this R is the resultant abstract state produced from our encoding from the kernel. This is where our LLVM to SMT pass comes in, and it better be the case that Z is a member of R. Okay? So now what has happened is, fast forward to present times, like Linux kernel developers are using Agni to check the soundness. So now let's say there is a developer who pushes a commit to the Linux kernel, and they use Agni and it says sound. Now should we accept this patch, the new abstract operator, or not? And typically why would someone commit a patch? Because the developer says, oh, it accepts a previously rejected program. It's improving the precision. Okay, just because you accepted one additional program, should you add it to the kernel? It may be rejecting other programs which was previously accepted by the original abstract operator. So this is where this paper comes in. So how do you compare? Like when you have two sound operators and they are all deemed to be sound, how do you compare one of them? How do you measure precision? How do you add precision testing to Agni? And whether this improvement is in precision is actually realizable in practice. Sometimes like all we are saying is, oh, there exists some abstract state where you are like precise, right? It may not matter in practice if the inputs are all preconditioned. So that's what I'm going to say for the next few minutes. So what does it mean for an operator to be precise? Let's say we have an abstract operator F1. It takes two abstract states and produces a resultant abstract state AV. It is the existing operator in your kernel. Okay? So you have a new abstract operator coming in your patch F2. It takes for the same input abstract state, it produces AV dash. I can say F1 is more precise than F2 if AV is ordered according to AV is like better value according to your lattice order compared to AV dash. And to formalize this as a formula, if this operator is true is more precise for all input abstract states. In this case, we have TU belonging to concrete values, ATAU belongs to any abstract state. We want the inputs to be well formed, so T is a member of AT and U is a member of AU. If this precision holds, now F1 is a much more precise operator for all inputs abstract state. Ideally, this is what we want to seek out. But sometimes what happens is when we run this query with an incoming patch, we get a counterexample. That means this operator is not precise for some input state. So what does it imprecision mean? There exists some input abstract states where this operator is imprecise. Now the question is this imprecision realizable? Okay, why does this matter? So this is because kernels does not start, the eBPF verifier does not start analysis from an arbitrary state. So let's say this is the set of all abstract states for your program. So what does imprecision mean? So you have these two operators, there exists two states P and Q where the imprecision actually occurs. Okay? But the kernel verification starts from a set of initial states. Now how does the state of the verifier evolve? It evolves by executing other BPF instructions or other BPF operators. Now what we are trying to do is to seek a program that drives the verifier from the initial state to this state P and Q where the imprecision occurs. And such a program, we call it as a witness. And now when you have an operator, you commit a patch, we want to identify, are there witnesses which actually demonstrate improvement in precision? And how do we synthesize these witnesses? This is where the second contribution of our paper comes in. We call it differential synthesis for witnesses. So we want to synthesize a BPF program that shows where precision matters. So what are we going to do? Going by the conventional idea in the program synthesis world, we are going to do enumerative program synthesis. We are going to enumerate BPF programs to a particular depth. In this case, I am going to enumerate BPF programs of length 2. Okay? So the first n-1 BPF instructions can be any instruction. The last instruction in our program is the operator of interest. Like we have a new operator for AND instruction. The AND will be the last, BPF AND will be the last instruction. So, okay. So I just enumerated using a regular depth driven enumerator. So, and why am I calling it differential synthesis? This is the concrete program. Okay? So I'm going to, what is the verifier going to do? Verifier is going to run an abstract program. Okay? So which mimics the concrete program. So it has the same abstract operator corresponding to the concrete instruction that you have, and now we have two such abstract programs corresponding to, one corresponding to abstract operator F1 and other corresponding to abstract operator F2. Now what we need to do to generate a witness is connect the data flow such that you can execute it in the kernel. Okay? So to connect the data flow, how do we do this? So what are the inputs to the first abstract states? So these are the kernel starts verification from a set of initial states. The values for this operator are these initial states. And then what do we want? The concrete operator. The concrete operator, the inputs to the concrete operator should be a member of these states. And we want the operator to be sound as well. So the result should be a member of this state. And for the second instruction in the program, what are the output states? The input states are either the initial states or whatever is produced in the data flow from the previous instructions. And we want both the operators to follow the same thing and the concrete program to follow the same thing. And we want the results to be sound, like both the operators are sound. We want the result to be contained in the resultant abstract states. And what we really want is the precision should be different. And this is what we seek out to. This is what we set out to achieve. So what I'm showing is like how do you, like given two sound operators, the two contributions of this paper are how do you test precision and how do you synthesize a witness. Using this, we synthesize a new BPF multiplication operator. Now it's part of the Linux kernel running as part of the core, and the witness that we generated was actually crucial. Since I'm running out of time, I'm not going to delve in, too much into the details. So what is the insight of the operator? When you're multiplying two input values, if the inputs are greater than 32-bit maximums, you can potentially overflow. The Linux kernel was unbounding the bounds. What we said is you don't have to unbound all the time. You unbound it only when such an overflow occurs. We checked it with Agni, and it's much more precise. And this is the witness that we generated, which convinced the kernel developers. So our paper has a lot more details on all the patches that we verified. Since I'm out of time, I'm going to conclude. So what is the key message? So we have been collaborating with the kernel developers over the last 6 years. So Linux kernel developers really care about formal methods. They care about safety and security of the system. If you are willing to work with them, this is a great opportunity for this community to engage with them. There are a lot more. Like what we have done is a very small slice of what are the things we can do as a community to make Linux kernel really safe. So what we added is Agni is just one small step in this direction. So if you are interested, look at our prototypes, and I want to thank the sponsors. I'll be happy to take questions now.
Thank you. Maybe we have time for one question. Yes, so yeah.
Okay, so thanks a lot for the very nice work and presentation. I was wondering, so you just mentioned testing for precision improvement of operators. Are there cases where you don't want to do exactly the opposite of that? So I will give an example. When you have widening operator involved, it could be that sometimes, like because widening is not monotone in a second argument, that in order for the analysis to be more precise, you need actually to deteriorate the precision of some operation or to lose precision earlier. And this is very counterintuitive fact and very hard to reason about. So if you are looking into precision improvement, you may actually miss cases where you actually want to kill precision to get better precision.
That's a great point. So Linux kernel, traditionally what do you do? When you have a loop, you merge information from various things by widening. And Linux kernel's eBPF verifier uses a totally different approach. It does not employ widening. It symbolically enumerates every path. So you may be aware of a cool verifier called Prevail from Muli Sajiv's group a few years ago. It widens. And what happens, like in a funny interaction with Microsoft's BPF team, they were saying there were programs which were rejected by Prevail because the widening was losing information. So in retrospect, the kernel developers are not static analysis experts, but still they came up with a very good pragmatic choice which improved the precision.
We don't have time for any more questions, so let's thank Santosh again.